Well, good morning, everybody, or if you're dialing in from another side of the world, maybe even good evening. It's wonderful to see how many people we've got signed up for what I know is going to be a really interesting discussion. We've got two very important topics to cover today. One is around location intelligence and the GeoInsurance of understanding where things are, one of the fundamentals of any kind of risk assessment. And then, of course, what is the impact of the changes in the climate and how does that impact future modeling? So we've got a great number of speakers for you. In a minute, I'm going to hand over to Richard Garry, who's going to take us through a little bit about what Gamma are doing. We'd love to take your questions as we go. We may cover those at the end. We might take a few as we go along. So hang on to your seats. We've got a lot coming in 1 hour. I have got the presidential mute button if any of our speakers get too enthusiastic. So we'll try and keep everything on schedule and have a bit of fun along the way. So with that, Richard, over to you to tell us about Gamma.
That's great. Thanks, Matthew. Good morning, everybody. My name is Richard Garry. I'm the Chief Commercial Officer at Gamma. So welcome to today's webinar on climate change and its potential impact on property across Ireland and the UK. There's been a lot of focus on this area, I suppose, in recent years, and with the availability of more data, Gamma wanted to try to understand how this might potentially impact our clients in the insurance and lending sectors in the future. So with that in mind, we've produced a white paper that Richard's going to present today. Some of you may be unfamiliar with what we do, but to give you some context, Gamma is a cloud-hosted solutions provider that integrates software, data, and services to help our clients reduce risk through location intelligence. Gamma have developed Peril Finder, which is our underwriting address level risk assessment and reporting solution that also incorporates web services for likes of form pre-fill and rebuild cost calculation. Peril Finder includes premium rooftop level geocoding, map visualization, intuitive risk and accumulation scoring, all to allow our clients access data quickly and easily through our user-friendly dashboards. And through our partnerships with companies like Ambiental and Terrafirma, Gamma endeavour to offer a single platform for peril data across these islands. You can find out more on our website, gammali.co.uk. So thanks for taking the time to attend today. I'll hand you back to Matthew, who will introduce our first speaker.
Thanks, Richard. Well, I was so enthusiastic to get you on stage. I didn't give you a proper introduction. So just for those that don't know Richard Garry, Richard is Chief Commercial Officer at Gamma and has over 20 years of experience in providing geospatial risk reduction solutions. Thanks, Richard. So another Richard, also from Gamma. So Richard Cantwell is Senior GIS Consultant with Gamma, and I'm going to be talking about some of the research on climate change and property data across both Ireland and the UK. And Richard's got 25 years experience in spatial analysis. In his spare time, he is, I believe, one of Ireland's foremost contributors to OpenStreetMap. So Richard Cantwell, over to you to tell us about what you've been doing in your research on climate change and property data.
Thank you very much, Matthew. Yeah, in Gamma, we've been working across Ireland and Britain on looking at how climate change is going to impact properties. We've produced a number of papers in this area over the last year or so, building on previous research that we've been doing. And I'm going to take you through some of the inputs into those papers, some of the models that we've been using, and some of the trends that we've uncovered and some of the details on what these impacts are going to be. I'm not going to go into the details of climate change too deeply. We have a speaker coming up later on, Barry O'Dwyer, who's going to bring us up to date on what the trends are and what these numbers actually mean. But I think a number of us will have seen, a lot of people will have seen, graphs, hockey sticking upwards and very rapid increases in temperatures and the amount of energy that is in the atmosphere and the oceans and on land. And we've seen temperatures. I mean, this is a great visualization of it here, just looking at rising temperatures. And this is going to have, obviously, major impacts. When you look at the published research coming from the likes of the Intergovernmental Panel on Climate Change, A lot of this is driven by different scenarios, and there's 4 main scenarios used in the research, and they range from a scenario of extreme carbon cuts, which will see a temperature rise by 2050 of 1 degree centigrade, all the way up to a business as usual scenario where things continue to on their current trajectory, which will see a 2 degrees rise by 2050, but that will continue to accelerate into the future. And with this additional amount of energy in the atmosphere, in the oceans, that has major impacts. So one of the key impacts is going to be flooding, and another one on subsidence. And we're going to hear from 2 of our partner companies, Ambiental and Terrafirma, talking about that shortly. But first of all, I just wanted to bring you through something that we did ourselves in Ireland. We looked at extreme sea levels. This is something that is going to become much more prevalent in the future, where we're already familiar with the high tides, and if you have a spring tide, that's above the high tide level. But with storm surges kind of inundate some parts of the coastline, but with sea level rise, that's going to become much more severe. And the storm surges and other extreme events are going to add to that even more so. So we're going to see, depending on where you are around the coastline, anything from 1 to 6 meters of additional water above the standard high water mark. Looking here at Dublin, for example, on the left, we can see that large parts of the commercial districts are going to be inundated in a worst case scenario. The same is true on the right-hand side there in Limerick, and large cities tend to be built on the coastline. So in Ireland, we're seeing major impacts from this in these worst case scenarios. What we've done is try to put a cost on this. We know the average payout for an insurance claim, whether it's a residential property or a commercial property. We now know, through the power of the geocoding and the address databases that are available, which buildings are inside these potential flood zones, and we can map them out. And what that gives us is, by 2050, potentially at risk in terms of claim volume in Ireland, just the Republic of Ireland, €2 billion, which is well in excess of what the current risk levels are. And if you look at the different levels of transactions and so on in residential transactions, we can see increasing numbers and volumes of transactions in these floodplains and areas that are at risk of coastal flooding. So in Ireland, we just really looked at the coastal flooding, and it was research that we did ourselves with our own data, leveraging mostly open data, but there's some commercial data sources in that. We widened things out then when we moved to conduct similar research in Britain, because there are already commercial providers, Ambiental and Terrafirma, who can provide us with much more detailed data in that area, and they can cover a much broader set of climate change topics. Looking at Ambiental, for example, we had a focus in Ireland on climate change driven extreme sea levels, but there's also increased flooding through rainfall and river levels rising and so on and so forth. So there's a lot more to it. So looking at the Ambiental FloodFutures product, we took that in. It uses a range of scenarios built on the UK CP09, a range of different time frames and the types of flooding. And we used the high emission scenario for 2050 and combined that with the open UPRN data from the Ordnance Survey Great Britain. And what we were able to do with that then is, using this open UPRN data, we made a modeling exercise to estimate the number of properties which are on a ground floor in a building, because obviously flooding disproportionately affects ground floor properties over second, third, eighth story building properties on high-rise buildings. And we can marry this. This is the Ambiental FloodFutures data set overlaid on top of OS Master Map and Open UPRN. So we can pick out the buildings that are going to be impacted by this. And what we've done then is looked at the proportion of properties in these districts which are at risk. And you can see the broadening of risk into new areas, and in areas there is already large numbers of properties at risk, these will rapidly increase. So by 2050, there's whole swathes of the UK which are seeing minimal amounts of risk at present from flooding are going to be potentially impacted by it. And again, just to put some numbers on that and where these are, the biggest uplift, this is the second from last column there, the additional percentage. Portsmouth, for example, currently has 5% of its properties at risk. But by 2050, an additional 16,500 properties to Portsmouth, which represents 16% of the stock in that area, are going to be at risk, meaning 21% in total. So the biggest uplift in terms of risk is typically along the south coast and along the east coast, along with some parts of London. And again, the exposure currently is around 72 billion in terms of claim volume, but that by 2050 that could rise to 122 billion pounds of potential risk exposure. And again, I should mention that these do take into account, or they do not take into account, flood defences, with the exception of the Thames Barrier. That is in there, and it is protecting large parts of London. Even so, you can still see that Merton and Kensington and Chelsea will see some impact. These are just the top 10 areas. We also looked at the residential transactions in there, and we can see that there's millions. Just in the last year, 2019, there was 13 billion worth of residential transactions in these impacted areas, with an average value of £350,000. So the volume of transactions in the residential sector is rapidly escalating, and when you consider that about 60% of first-time buyer mortgages are 25 years and above, the likelihood is that if some of those properties are being taken out by first-time buyers, those mortgages are going to be still outstanding by the time we're likely to see these impacts. We also looked at the area of subsidence with Terrafirma data. We used, again, it uses a range of scenarios and timeframes, and it can contain soil movements from a range of sources, including soil shrinkage, coastal erosion, vegetation, historical mining. Tim from Terrafirma will talk about that shortly. Again, we used the high emissions 2050 and combined this, as before, with the OSGB open data. I'm sure Tim will probably have this slide in his presentation, but it's just looking at the areas where there's a large number, or large proportion of the soil is clay-based, and it's going to lead to soil subsidence hazard increases. And we can see this and there's a lot of other additional hazards in the Terrafirma data, whether it's tree canopies, sinkholes, and historical mining and the like. But again, like we did with the flood data, we can combine this with the address databases and spot the patterns then in changes in risk from today up to 2050. And it's a similar story, although the different areas being impacted. Large increases in areas around Britain are going to see subsidence impacts. And the issue, I suppose, in one respect is that in some of these areas, builders and engineers are familiar with dealing with subsidence because it's been something they've been working on for a long time. But there are areas there where subsidence currently is not an issue, and it's going to become much more severe in future. So the potential impacts there are large. And again, similar table to before, we can see the districts which are going to see the largest increases. Swindon, for example, currently has a very, very small number of properties at risk, just currently about 1,300. By 2050, that's going to be 85,000. So they're going to go, currently 1% of the properties in Swindon are at risk of subsidence. By 2050, that's going to be 80%. So massive increases there. Now the costings on these, well, your average subsidence claim, the average subsidence claim has a lower claim volume than a flood, but they're much more prevalent. The current exposure is 41 billion around the UK, claims exposure, rising to 53 billion by 2050. And the current average annual loss to the insurance industry from subsidence is around 60 million pounds a year. And we estimate by 2050, that's going to rise to 155 million per annum. And again, looking at the residential transactions, it's a similar pattern to what we've seen with the floods impacts. There's large volumes of transactions, 21 billion pounds worth of transactions last year in areas which are going to be at risk of, newly at risk of subsidence by 2050. So our future developments in this are going to be, we're going to be rebasing models, new scenarios using higher resolution data, LiDAR-based digital terrain models and digital surface models, certainly in Ireland. Also the soil mapping, using more detailed soil mapping in Ireland, and building on the models that are continuing to come from Ambiental and Terrafirma. And we have additional models under development. So thank you very much for that. If you haven't already downloaded our white paper, you can get it on our website, gammali.co.uk. And with that, I'll hand back to Matthew. Thank you very much.
Thanks, Richard. That was fascinating. I certainly felt I learned a huge amount there. So you have left a couple of minutes of questions. We've got a couple of questions coming in from the audience. I'm just going to take one of these because one of them seems quite a technical one. Well, they both are actually, but one's less technical than the other one. But David Dodd has asked, you've used projections based on UKCP 09. The, I guess, updated projection was released last year, UKCP 18. Just wondering, the question is really why they use the older ones, and maybe are you planning to update with the new projections?
Well, actually, that's something that we can probably ask Ambiental and Terrafirma, because those projections were in their models. But the one thing I would say is that building these risk models is not a trivial exercise. It takes years, possibly, to fully generate these models out. So working on what was best available when these models were first being built, what the CP09 was the standard at that time. And I do believe that both Ambiental and Terrafirma are seeking to update to UKCP18. But the issue, I think, there is that some of the climate change or impacts that we've seen just this year are already calling some of the projections in UKCP18 into doubt, in that the future scenarios might be even more severe than that. So there may be some possibility that there could be a mid-cycle revision to UKCP18. So I'd leave that slightly to Tim and David. Maybe they might want to comment on that in their pieces. But it is something that we're aware of, certainly. But it's just what's out there and what's changing in the marketplace. Okay.
Well, great, Richard. Thanks. That's really helpful. So just given the time, I think we'll just switch over now to Tim Fairwell. So Dr. Tim Fairwell has got a passion for helping insurance organizations and banks and other institutions manage the risk across a whole different series of risk types. Tim today is talking to us with his Terrafirma hat on, and we're going to be picking up on what Richard's told us about substance and going into that in a bit more detail. Tim, just in terms of timing, you can maybe pick up that question about UKCP in there. If you could, you can sort of do it justice quickly, but I don't want to distract too much from your conversation. But I'm very interested to learn about this, because we heard a lot about substance about 20 years ago, and it's really interesting to see that it's now coming back into the sort of view as a big issue. So with that, Tim, over to you.
Okay, brilliant. Thank you so much. It's a great question that you asked about UKCP 18. And it is, definitely something that I'm working on. Even last night and this morning in the early hours, I was bashing through more very large data sets, causing my computer interesting problems. It does take time. When we did the UKCP 09 project, that took about a year just to process the data. And there are issues with 18 in terms of some missing data here and there. We look like we're on track probably to get the first model out before the end of this year. So we've made phenomenally faster progress this time. And it's something which is occupying a lot of my thoughts. So yes, it's on its way, and it should be here before too long. But okay, in terms of subsidence, this is something that I'm crazily passionate about because for me, it's this interaction between the weather and the soil and the built environment that's so exciting. You know, Richard was talking earlier about climate change. Is it actually changing? There are still people in the world who don't believe that it is. I think the science strongly disagrees with that. And if you look back through time, starting in kind of pre-industrial times and moving forwards, you see this red line, and this is looking at effectively the average temperature in the middle of England. You know, once we get past industrial times, you know, this line just goes up and up and up, and that trajectory looks set to continue. Now, when we're looking at, you know, last year's weather, and this, you know, or a specific weather event, we put that in one camp. We call that weather. And when we're talking about climate, it's a bit more kind of longer term trends. So just bear that in mind. You know, just because you have a hot day or a really wet day isn't necessarily that's climate change. You know, there are these fluctuations in day-to-day and week-to-week weather patterns, but climate change is much more about the gradual long-term trends. And that's what we're talking about now. So if we look, how far have we come so far? Probably about 1 degree warming over pre-industrial levels across the world, but it's at 1.5 that catastrophic change starts to occur. But a lot of the companies that we're working with are looking, you know, at more extreme scenarios and saying, well, how will 2 or 4 degree warming impact our business, and making, you know, plans now so that they can cope and be viable businesses under those horribly extreme scenarios. In terms of why the climate's changing, I think we all know this by now. We're looking at things like meat production, dairy, transport emissions, and so on. And all these greenhouse gases act as a blanket around the Earth. And radiative forcing is a kind of a nice term that looks at the amount of energy that's coming in and the amount of energy that's leaving the Earth. And as that blanket keeps more of the energy in the Earth, it warms up. And that's what we mean by global warming. So how does this impact on climate change impact on subsidence? Well, I'm going to give you a couple questions that you need to bear in mind. The first question is, can the soil shrink as it dries? And I've got here a little experiment I did with my kids, which you'll recognize some building blocks here. What I've got is 3 different soil types, and I've added water to dry soil. And what we can see here is sandy loam doesn't expand, but clay loam does expand as it absorbs this water. Sandy soil in the middle will kind of wash out. And subsidence is effectively the opposite of this. So imagine they're wet soils and they're now drying. And you can see here the clay soil drying and subsiding. It shrinks, the volume shrinks, whereas the sandy loam soil doesn't. Okay, so this is just demonstrating that different soils respond in different ways to the removal of water. So we see sandy soil washing out and clay loam expanding. Okay, so what we do is we look at the map, we look at the soil, and we go, well, which of these soils have this shrinkable potential? And we have a map that answers that question. Now, when you have a house that's built half on sand, half on clay, that's like trauma zone, because you have differential movement. So some of the house might be going down more than others, and this differential settlement can cause cracking and subsidence. And it doesn't even need to be those hugely extreme soil types for this to happen. It can just be that you have a tree in close proximity and it's clay underneath the whole house, but that tree extracts more water from that one side and the house will subside. So the first question was, can the soil shrink and swell? The second is the weather going to be hot enough and dry enough to realize that shrinkage? Because where you have shrinkable soils and hot and dry weather, that's where you have problems. So this is where the climate models come in, and we look at and we say, well, which parts of the country are typically hot and typically dry? So the red ones here are those which are hot and dry. And we take the first question, can it shrink? The second question, is it hot and dry? And stick them together, and this creates our hazard map for subsidence. Now, the third question is, how is the weather going to change in the future? And as Richard's already said, we've got changing weather patterns. More of these soils are going to become prone to subsidence. So we're going to have more issues. So this is looking at, again, the UKCP models, the nine versions, but we're just seeing this trend of this hot and dry part of the country spreading across more and more of the UK. So what will this mean in terms of future? Well, we're looking at new parts of the country really being exposed. And as Richard already pointed out, we've got these in the northeast and in the southwest, properties which have not previously been prone to subsidence. Suddenly, the weather is so hot and so dry that these properties are now likely to move, and they won't have been remediated. So their actual exposure is probably greater than those in the southeast, where subsidence has been a problem for years and years. In terms of number of properties at risk, where we're looking, kind of present day around 12-ish%. As we go through the 2030s, 2040s, it's about 19%, and it increases a bit more even after that in the 2050s. So with this country, as more and more of these soils dry out in the summertime. Now, I've pretty much run out of time. I just wanted to point out, it's not just subsidence. Extreme weather events are becoming more and more problematic. These are going to impact not only inland areas, but also we're seeing huge increases in coastal erosion. So part of our models is also just looking at the exposure of coastal erosion, and this is I think the 1950s. This house, the third one along, its position now is here. So this is another really important issue that we consider in our models. So it's not just subsidence. We're also looking at increases in coastal erosion, increases in landslides and landslips, and also mine collapses and sinkholes. And these are all kind of combined together in our new model, which we're releasing, which looks at all these hazards together, and we call that NGRM climate. So that's a kind of whistle-stop tour from me. But yeah, any questions coming up from that?
Well, Tim, that was fascinating. You always manage to cram an awful lot into a short time, and I'm now going to go outside and dig up my garden and see what kind of soil I've got, if I can borrow some Lego bricks off my children. But just one question which coming from the audience, just asking: are your slides going to be available to share with the audience?
I'm sure we can do something like that. Yes.
Good. And then another one from me, actually. You showed that very interesting graphic of the different soil types, or even within an individual building. How high resolution is the data that's now available on soil types, so that if companies are looking at the risk to properties, can they trust what they're seeing in terms of soil types, or is it more on a property by property assessment?
Oh, that's a really, really good question. Any soil map has a huge amount of variability in it because of the way that soils are mapped across the UK. So there's about 1,000 different soils across the UK. And to map those all at high resolution is pretty it's virtually impossible to do at an economic level. So the way that we build the models is we look at variations. We map those 1,000 types and group them together into what are called soil associations. So groupings of soil types, which are commonly found in association with each other in the landscape. And then what we can do is we can cut that model and say, well, in this group of soils, in this street or this, cluster of houses, what percentage of those are highly shrinkable or not? So what this allows you to do is to build up a kind of risk appetite, a model customized to your risk appetite. So you can say, well, I want to exclude all properties where there's any chance of having highly shrinkable soils, or actually, I can tolerate maybe 20% shrinkable soils. So there is uncertainty in the model. There's always uncertainty in a model. But what we like to do is just make sure that, when you are training your model, you can say, well, this is even more at risk than these ones. So
great. Well,
a lot more detail, but probably in another point.
Yeah, feels like a whole session on that. No, thank you very much. It was really helpful. So I want to move on now. We've got David Martin joining us. David from Ambiental RHDHV, since they got taken over recently. And David's got over 15 years experience in catastrophe risk generally, and is going to be talking to us today about the work he and his colleagues have been doing around FloodFutures, looking at, well, as the title suggests, the future of flood. So David, with that, over to you.
Thank you. Thank you very much. So just addressing the question very quickly about UKCP 09, and then I'll jump back to the presentation. So FloodFutures has multiple different outputs. In a nutshell, our financial sector products are fully updated to UKCP 18, so that's ALs and risk ratings and so on. The mapping, so this is essentially rebuilding the full UK flood map at 5 meters from now and then again into the future. It takes a bit longer to update, so that's nearly there. But of course, it's a huge effort. So that's why. And this study was done on homogeneous mapping across the whole country. So that's hopefully the shortest answer I can give to that. So yes, so David Martin, I'm CTO at Ambiental. I'm trying to cram in quite a lot of information into 5-6 minutes. But let's just start by thinking, why do this? So what are the questions we're trying to answer with flood? Now, most organisations will have a pretty clear idea of their current exposure to flood from one source or another. And we're really looking at, the obvious points, like how much worse might that get into the future, but also, flood is very granular. So how can we dig into that and understand the spread or the uncertainty of that change of risk? Where is it changing? Why is it changing? And ultimately, whoever I am, whether I'm planning pipelines for a utilities company, if I'm looking at regulation as a bank, trying to look after a portfolio as an insurer, do I need to change my strategy, or should I think about changing my strategy towards flood over the short term, the medium term, or the long term? And how confident can we be over changing that? So we're just focusing on UK for this one. Obviously, UK benefits from some fantastic science in UKCP 09 and 18. And when we build our futures products, we like to characterize a sort of high, medium, and low emissions scenario set. What this is essentially doing is saying, this is the worst case, this is the best case, and this is the, well, we can use the word probable case, but medium case is more accurate. The concept here really is that whilst you could follow a single pathway into the future, it's helpful when making strategic decisions to understand how much that could, in theory, vary. So our high, medium, low emissions paths generally track the 8.5 RCP 6, and now 2.6 under UKCP 18. It used to be 4.5. Now, if we think about what a climate model is, so climate models model continuously into the future, hour by hour, second by second, and look at the variation, or essentially recreate the weather system, the climatic systems, and what is going on the ground. And that means that when we think about a point of time in the future, actually, we're generally thinking about a chunk, a multi-decadal chunk of time in the future. So to put that simply, the 2020s actually covers the period of time from 2015 right up to 2039. So essentially we're thinking of recreating those river gauges and rainfall gauges, but synthesizing them into the future, and then working out where you're at that stage. So this gives us 9 future points that we can then draw between, and we can interpolate between these to understand how that change looks in a more granular way. But essentially, yeah, we've got 10 flood states, 3 epochs of time, and 3 different emission scenarios, and that's what we're producing. Good. So how do we turn a climate model into a flood model? And there is a lot of science in between one and the other. Now, again, in the UK, there's a fantastic amount of science that's been produced by organisations like CEH, the Environment Agency, NRW, SEPA, UPWER in particular. And a lot of these outputs are fantastic at helping us to translate the metrics that climate models output, so things like general rainfall over that period, temperature, of course, and turn those into the key metrics that we need to change in a hydrological model and then a hydraulic model. So what we're ultimately trying to discover is, how does the peak river flow change under these different scenarios? We can do that. We can think of that as a percentage to simplify it. But in order to get there, actually, there's an awful lot of science that we don't really have time for today that needs to be undertaken to try and get some concept of how that would change. And there's a lot of uncertainty around that, of course. Things like sea level rise, a little bit more direct. So you can imagine that it could be pretty quickly and easily adjusted within a future model, but fluvial particularly, and also anything to do with storm surges is quite tricky to translate one into the other. Good. So just a quick highlight of how the mapping product looks. So this is the 100-year flood map for 2017. So the now, essentially the present day, 1 in 100 year, based on our recorded baseline of data. We push that into the 2020s under the high emission scenario we're looking at the moment. So this is RCP 8.5, and we see actually a meaningful change there between the two as certain cells of the floodplain start to activate. If we then move that forward right up to 2080 or the 2080s, that starts to look a lot more like what we know now as the 1,000-year flood extent. It's filling up the entire floodplain. The depths are significantly increased, the extent is significantly increased. So that's quite representative of what we're seeing over the country. So if we look at that another way, this is the data extracted to buildings now. So just looking at anything exposed to a depth of flooding of any, well, anything above, I think it's 10 centimetres. And if we take the medium emissions scenario, we'll share these slides, of course, so I'm not sure I've got time to go through the right-hand graph, but on the left graph, we've got a medium emission scenario moving forward in time from now. If we just look at the 100-year event, so this is the high-risk floodplain, not any floodplain, but the high risk. It's about 1 in 9 properties that are at risk right now, and that changes as we go forward through RCP 6 to 1 in 6 by the end of the century. And that's quite startling, because that 1 in 6 number is what's pretty well agreed in, at least in England and Wales, that is the number of properties that are at risk from any flooding, from extreme flooding right now. So that was the sort of headline statistic that really made us open our eyes in a big way. Now, there's a lot of nuances to this, and we could spend hours, but I realise I've probably got about 30 seconds left. So I'll just flash up this last slide, which is one of the other ways to look at this data is to turn it into average annual losses. You could use changing risk ratings for banking, changing annual damage ratios for accurate insurance loss estimates. And this way you can, so this is actually a portfolio of 100,000 properties that's been run through the model, and we're just looking at all of the different scenarios against all of the different mechanisms of flooding and combined. And this is quite a helpful way to just show the uncertainty that we're dealing with, and where that uncertainty comes from, but localized to that specific set of properties. Flooding is a very local peril. You can look at one group of 100,000 properties and it can give you a very, very different reading in future to another group of 100,000 properties. So that's why we're always keen to do building level analytics wherever possible. So I'm going to leave it there, and I think stop sharing. So thank you very much, and happy to answer any questions.
Well, thanks, David. No questions from the audience for you yet, but please do keep putting your questions in, because we're going to come back at the end. And just given the time, David, I actually have got a couple of questions for you, but I think we'll leave them to the end.
Sure.
And move it to Barry now. So just make sure we give Barry a chance to tell us what he's been up to. So just introducing Barry O'Dwyer. Sorry, Barry. Barry is from, I'm going to have to read this, like if I memorized it, I would get it completely wrong. But Barry is from the Centre for Energy, Climate and Marine at University College Cork. He's got a lead role in researching climate change impacts. He consults to governments and others for decision making, and as you can see, he's going to tell us his view on climate change and adaptation, and basically bring together a lot of the themes that we've been talking about already. So with that, Barry, over to you.
No, thank you very much, and yeah, now delighted to be here again this year to present at this. And yeah, so I'm coming from University College Cork, where I lead the development of Climate Ireland, and I also lead the Impacts and Adaptation group there as well, a research group. So what I've been asked to do today is just give you, I suppose, an overview of the science around climate change currently, and also where we're going in terms of our responses in relation to, I suppose, what's the future science telling us, and then in terms of our policy responses, what kind of trackways are we going on to achieve them. So it's quite a task to do in this short space of time, but I'll do my best. In terms of the science, I think we can obviously just look at future projections, but ultimately the observations provide a really useful way to look at how our climate is changing. And we always refer to global climate change. So what this animation does, you may have seen it before, is it shows for a large number of countries how average temperature has changed relative to an average baseline temperature calculated over 1951 to 1980. Just to give you an idea, this is Ireland here, this is UK. Red means above average temperature, blue means below average temperature. The size of the circle dictates, it tells you how much it has changed relative to that average temperature. So what you can see through since industrial times, a lot of variability in temperatures across all of the different countries included in this through to the 1950s. And then as we move into the late 1900s towards the 1980s, 1990s, we start to see more red appear. So this signals what we would call anthropogenic climate change. It is becoming clearer and clearer into the early 2000s, and all countries are now showing what we consider to be above average temperatures. And for Ireland, we can see there a 1.1 degrees Celsius increase above what we would consider to be our average climate. So our average weather, and similar for the UK, 1.2 degrees Celsius. So we can refer to climate change as a global challenge, but it's also very much a national challenge that we are all going to have to plan for, not only for flooding and subsidence, but heat waves, etc. So in terms of the evolving science and policy, I think this is a really important thing to look at. So we have the Intergovernmental Panel on Climate Change, which is the global authority in terms of climate science. It was established in the late 1980s, and through time has produced a number of assessment reports that essentially synthesize the available scientific information and data on our changing climate through a number of assessment reports. First one in 1990 right through to the most recent in 2015 overall assessment report, and then 2018 where we look at 1.5 degrees. And now we see a new assessment report coming in 2022, which will result in a whole heap of new climate data. Through time, the message hasn't changed. The trajectories of observed and projected change have stayed the same. So the science is settled right back since 1957, when we first started to look at warming of the climate system. Interestingly, in 1988, we had the studies on the implications of climate change for Ireland. In tandem with this, we've seen an increase in policy at the international stage, starting right back from COP1 in 1995, But this has really ramped up recently through the Paris Agreement in 2015. This is, and the Agenda for Sustainable Development Goals. A key aspect of the Paris Agreement is that it accepted that by addressing the causes of climate change, we were still going to have to deal with climate impacts that are already baked into our system due to a long history of greenhouse gas emissions. So there's a certain level of radiative forcing that we are going to have to adapt to. So what I'm showing here is we're moving into the future. As was suggested, this comes from the IPCC AR5. These are the projections of change, RCP 8.5 being a high level scenario, RCP 2.6 being a lower level scenario. So even at a lower level scenario, we're still looking at nearly we've already achieved a 1 degree rise in temperature, but that will continue. And similarly with sea level rise up to a 1 meter sea level rise under RCP 8.5 by end of century. And now this is being produced to contribute to the upcoming AR6 reports, the IPCC assessment report by colleagues in the Irish Centre for High-End Computing. So they're using what's called the EC Earth model here to simulate what future climate change might look like. And again, now we can see obviously both SCP 2.6 is a lower emission scenario compared to a higher emission scenario. And as we move into the future, we can see both are quite similar. And that is something to 2050. That's when we expect to see big divergences in levels of climate change as a result of our emissions of greenhouse gases. So we can obviously see there's a lot more warming at the poles under the 8.5 scenario, the high emission scenario, and this is the result of melting sea ice, albedo effect, and general circulation resulting in increased temperatures. So regardless of our emission scenario, we see an increase above what we consider to be average temperature, and there's quite a difference in terms of both scenarios as well. So the science is clear. Climate is changing, has been changing, and is going to continue to change regardless of what we do around our emissions. And this, as was said, has implications for extreme weather events. So if we look at the this was recently published work in 1976 UK heat wave, and then compare that to the 2018 heat wave that you may remember, is a very similar meteorological setup. This was undertaken by UK-based researchers, and what they looked to do was see, well, if we had the 2018 heat wave again, a similar weather setup, plus 50 more years of warming under a relatively pessimistic scenario, by 2070, this is what that kind of heat wave would look like in terms of increases in temperature from a baseline. So quite large increases in the Northern Hemisphere, Southern Hemisphere, etc. If we achieve our goals in terms of the Paris Agreement and keeping less than 2 degrees Celsius above pre-industrial, this is what it would look like. So still far more severe than was experienced in 2018. So this is a key issue. Even if we achieve our goals under the Paris Agreement, we've still got significant climate change. And believe it or not, that'll actually result in heat stress in Dublin. So this is work that we undertook as part of the UrbanDoc project in Cork. And what I looked was changes in average temperature in July 2050 under a high level scenario of change. And it examined what we would call the urban heat island effect, where we see how urban areas increase average temperature in comparison to their surrounding rural areas. And what we found is that we're going to start to see issues of strong heat stress in Dublin city centre and surrounding urban agglomerations. So it's not only an economic issue that we face, it's actually a societal issue also in terms of older populations. So there's two kind of things we can do about this in terms of our responses, and globally and nationally the responses that are being taken. I think up till now it's been primarily based around mitigating, so reducing the causes of climate change through reductions in greenhouse gas emissions, and also enhancing our carbon sinks, peatlands, forestry, etc. But we now also have to think about adaptation to the impacts of climate change. Certain level of climate change is guaranteed, even if we stop emitting greenhouse gases today. But on our current trajectories, quite a lot of adaptation will be required. So this is done, a piece of work, you can find this actually, it's on the Climate Action Tracker. And what it looks at is where are we currently at in terms of our policies to reduce climate change and projected changes in temperature. So if we continue where we are on our current pathway, we're looking at 4.1 to 4.8 degrees Celsius increase by 2100, so far exceeding the 2-degree target. Our current policy set us on a pathway of 2.7 to 3.1 degrees Celsius. If we actually deliver on our pledges and targets, we're looking at 2.4 to 2.7 degrees, so always breaking this 2-degree barrier. This is the kind of emissions pathway we have to take. We have to start reducing emissions now down towards net zero by 2050 to achieve 2 degrees, and we have to do this even quicker to achieve 1.5 degrees. So currently, we're looking at significant change required. Uncertainty was mentioned. I think we can, and the Thames flood barrier, this is a very useful way of looking at how do we actually deal with this uncertainty. So when the Thames barrier was originally constructed in the 70s, it was expected to be closed every 2 to 3 years. Since 2000, it's been 6 to 7 times a year. And in 2013 to 2040, it was closed 50 times. How they developed their, essentially what we call an adaptation pathway, is a decision tree approach that's based on observing the maximum rise, the rise in the water level in the Thames estuary, and putting threshold values on this, on when they would have to start thinking about putting new defences in places. So they look at their existing system, then they start talk about raising defences, and that will be sufficient up to about a 0.5 metre. They're currently raising these defences. Once we start to think about a 1 metre rise, we have to start looking at new measures being put in place, such as we could do a new barrier raised defences, entirely new barrage, which will protect us up to 4 metre rise. So what you can see here then is they develop a pathway through these different approaches. That is, essentially new measures are implemented once threshold values are reached. So 1 metre that they aim to actually improve flood storage, restore interim defences, over-rotate the barrier, and then moving into a point that once they start to see 2.2 metre rise, they will have to start considering a new barrage that will protect us out to 4 metres. So it's a way of trying to address the uncertainty in the climate projections in terms of what is going to happen into the future, but it is based on a really sound monitoring and observation system around the particular variables of interest. So I think that is a whistle-stop tour of where we're at in terms of climate change. I hope it's not too too hellish in one respect, but I'd like to thank you for your attention then, and just say you can find more details about our work at climateireland.ie, and there's my email address and Twitter as well. So thank you very much.
No, thank you, Barry. Again, lots of really excellent information provided very succinctly, and as you said, very sobering in there. I guess a question from the insurance perspective, where clearly the insurance industry has a responsibility, like everyone else, for the longer term impacts of or reducing the longer term impacts of climate change. But on the short term, so like a 1 year cycle, are you starting to see signals or impacts on forecasting that can be used to look at different frequency of hurricanes or rainfall or wildfires and these other sort of catastrophic events?
I mean, one thing that is happening now is we're starting to see the growth of, and not an area that I'm involved in, but is attribution science. So they can start to look at specific weather events such as the 2018 heat wave and identify, well, what was the percentage of severity that we can actually attribute to anthropogenic climate change above what we would normally expect. And that work is really progressing, and there is a really good source of information that the Climate Change Attribution Centre, which is an excellent web-based resource that you can look at to find information on a really wide range of events.
Great, well, that's very helpful, thank you. So I'm just going to pass back over to Richard Garry in a minute, but just a couple of questions that came in whilst you've been talking we haven't yet had a chance to pick up on. So Tim, one back for you. So there's a question that came in from Alex Hood asking about the subsidence damage. Is that really generally caused by an extreme event in 1 year, or is this more of an aggregation of shrinkage and growth over multiple years?
It's a great question, and it's hard to give a definitive answer to that. I think what we've seen is you do get these event years where you have a huge buildup of claims across that year, but often they are preceded by a slightly cooler but also warm year in the year before. So it's like anything, it's a mixture, but you can get subsidence happening, in 1 year. But yes, what's happened in the year before does kind of prime it, if that makes sense. So it's a bit of both.
Okay, thanks. And then David, a question for you on the flood models and how you built out your projections. So anybody who's involved in flood modeling knows it's a very complicated process to look at all the factors from the rainfall and runoff all the way through to what comes in the front door. When you looked at doing your projection models, is there now a sort of consensus to use to actually model the impact from increased rainfall on and other causes of flooding on the outcome, or are you you've got two variables in there? One is actually the flood models that are used, as well as the different types of outcome in the future.
Just trying to understand the question. So is the question really looking at how do we decide on which metrics to use? Yeah,
well, there are different flood models out there in terms of you can take from rainfall, for example, to what actually causes a flood.
Gotcha.
Yeah, so is there a consensus now around those types of models, or is there still quite big variability on that side before you can get into long-term effect?
No, there's huge variability, but what you would tend to do, and this is it all links together to the point around flood being really localized and flood really you need to look at a pretty high resolution, because your one house can be literally at a completely different, a 100% different risk to the house next to it, which makes modeling very difficult. And that means the middle stage, so we say climate models turn into hydrological models, turn into hydraulic flood mapping tools. If we just look at the hydrology of today, you could use 5 different approaches in most catchments of the UK, in fact probably more, to come up with a design flow, a 100-year flow, a 1,000-year flow, or whatever. So is there a consensus view? The consensus is to understand your uncertainty as much as possible. That's really the one thing that everybody agrees on. There are certain models that are better suited for different environments. So, national scale modeling, you can't often do all of the local, take account of all of the local little bits of information and knowledge for each specific catchment, as you might do for a local engineering catchment study. It's difficult, and that's why these things need tested, and you need sensitivity tests, you need calibration. There isn't a consensus view on exactly the best way to do it. There are loads of different ways, but just test.
Okay, well, thanks, David. Well, Richard, back to you in a minute. I just want to say, from my perspective, thank you very much to all the presenters, keeping on time. I see a lot of these events, and this was definitely one of the highest energy, lots of information shared. I know the slides are going to be shared later. Congratulations, everybody, for getting a lot of learning into 1 hour. So, Richard, I'm going to pass back over to you, but one question for you, you might just answer in that, if you weren't already planning to, is, for all this great information out there, how does that then link into what you're offering or your partners are offering through Gamma in terms of sort of practical ways people can use this kind of insight?
Thanks, Matthew. Yeah, so I suppose what we're trying to do is get this data and make it available to our clients through our Peril Finder platform, so that they can plan for the future, really, and understand risk both now and how that's going to change. I think there's an understanding that people want to try and understand what's happening at this moment in time, but we really wanted to make people aware that things are changing into the future as well, and that they need to start looking beyond next year and really looking into the future 10, 20, 30 years. So I think we're almost there at this stage. I'd just like to thank everybody, thank all the speakers, thanks Matthew, and thanks for attending today. I hope everyone found it interesting. We'll probably leave it at that. I think we're bang on 11 o'clock. So with that, we'll say bye-bye. Thanks, everyone.
Thank you.
Thank you.
Thank you.
Bye-bye.
Okay.